sense this is a lesson in never throw away old data. When I was preparing the presentation, I looked through, and in fact, the data that we collected to do this piece of work was actually collected in 2006. We published a paper out of it, and then we went back and we learned some more, we did another paper out of it, so never throw old data away. Also, say thanks to the organisers who invited me, and also I've got Phil and Jean-Yves in the room, just say thanks to those two guys for getting me involved in tomography. I had more fun and frustration doing tomography experiments because they're being right than anything else. Okay, most of the work done here is done by Melvin Harvey, who's at Sheffield University, and Terry and George Thompson at Manchester, allows us to use some of their equipment. It's an examination of, if you really want to understand what a short crack is doing, what are the techniques available for getting into it. I'm not going to claim any great conclusions at the end of here, just what can you measure using the techniques which are available now. And it's bringing together a whole suite of things. Computed tomography, image correlation, we've had a little bit on those before. Diffraction contrast tomography, I'll introduce that for those who don't know it. Slicing and dicing with basically serial, it's a bacon slicer in an electron microscope. And then bringing together to try and say, well, can we study the crack opening behaviour of short fatigue cracks, both the opening displacements and the modes of opening? So can we look at is a crack a stage 1 or stage 2 crack based on its crystallography, based on its opening? So that's what we're trying to do. We've worked with magnesium. We've done it for several reasons. First of all, it's low attenuation, so it's great X-ray techniques. It's got a nice big grain size. It cracks in an interesting way, and particularly it has the high temperature magnesium alloys, which alloy with things like neodymium and other rare earths. They give you great contrast for tomographic techniques, which gives you speckle and features within the microstructure. I'll come back to this image towards the end. Very, very briefly, just on combined tomography and image correlation. I won't go into details, but just really to sell it as a fantastic technique for internally strain gauging your materials. We've been using it for a number of years, looking at, for example, sub-indentation cracking in ceramics, where you can measure crack open displacements and the deformation field underneath an indentation. You can look at complex materials like composites, and again look at damage within the microstructure. You can even look at plastic yielding if you have the right kind of material, plastic deformation underneath an indentation. So any kind of study where you're trying to measure deformation at the fine scale in 3 dimensions, I really would recommend these techniques. The key requirement, of course, is you've got to be able to get X-rays to it, and also you have to have speckle, you have to have a microstructure that gives you features. You don't need much, as the bottom right image shows you, don't need much contrast, but you need something. So unfortunately it's not a panacea, you can't look at everything. The other technique, which we use, and again it's another one indebted to working with Jean-Yves on this, is diffraction contrast tomography. And I have a couple of slides just to introduce what it is, but it's not necessarily a widely known technique. It's basically 3-dimensional EBSD. It's a way of measuring the grain orientations and grain shapes within a polycrystalline material before you destroy the sample. It's a non-destructive characterization technique. We've used it in a number of problems. We looked at stress corrosion cracking in the past, where by using tomography, one can observe the propagation of a crack through the microstructure. You can also measure the grain orientation and grain shapes, and use that to understand how the grain boundaries interact with the cracks, or vice versa. So what we did with Phil earlier. One can again look at integrating and cracking in the ceramic, where here we've got cracking because of the thermal stresses. And one way of understanding it is if you can bring in the microstructure, you can relate the locations of cracking to thermal expansion and cracking. So again, a useful technique for understanding how cracks interact with materials. And the basic principle is, it's a bit like using like transmission electron microscopy on a beam line. When you have the synchrotron beam going through your sample, if the grain is in the diffracting position, you'll get some of the beam being diffracted off, so you're losing some intensity, and you get a bright spot and a dark spot on your detector. You can use the information on the locations of those points and how they move as you rotate the sample to reconstruct the orientation of the crystal and the location of the crystals. It gives you information on the internal structure. We used it here in an experiment of magnesium, where we wanted to look at the behaviour of short cracks that initiated in particular crystals. So before the experiment, we scanned the sample using diffraction contrast tomography to work out the orientations of the grains, and we then took it back into the microscope and used focused iron beam towards a notch in the grains that we were interested in, so we could choose the locations of initiation of cracks. This is just an image of the kind of data you get with the diffraction contrast tomography. And you can see here, you have, there's a grain here which is diffracting, and there's the spot from the grain. There's another one there which is diffracted over here. Each of those spots, of course, is giving you the shape of the grain projection, and that's how you build up the three-dimensional information on the microstructure. Beautiful technique, as long as you haven't got too many grains in your sample. Ballpark figure around about 20, I think, across the thickness of the sample. But coarse-grained materials, really, really nice thing to do. The other technique, this is the one that I'm indebted to George Thompson for, is serial block face scanning electron microscopy. It's commonly used in the biological field, but for light materials. George has one which is good for looking at aluminium and magnesium, again, light materials, where you can slice the sample in layers around about 70 nanometers thick inside an electron microscope, take an image of a single slice, and then rebuild the structure. And one of the things we were interested in doing here was comparing the kind of information you get with high-resolution X-ray tomography with what you get if you then do destructive sectioning. How good is the tomography? The point we're talking about here is, do you see the full crack with X-ray tomography? Well, here we want to go back and look at the crack in more detail. So one of the purposes here is just to compare the quality of the data. So this is the crack that we're looking at. It's electron 21, it's an alloy for magnesium electron, neodymium, gadolinium, a bit of zinc in there. And that's the crack that we developed inside the microstructure. So the coloured grains are showing you the orientation of grains and shapes. We had a fit notch inside this grain, and then the crack propagated a couple of grains around. That's the crack. That's just segmented based on the grayscale level. So again, we can get that lacy appearance because where the crack is almost closed or the crack over displacement is of the order of the voxel, you don't really get any contrast. I had a very, very patient visiting scientist who went through all the tomographs and tracked the position of the crack front all the way through a series of scans. We had about 10 scans as we propagated the crack. What we were interested there was, first of all, what's the average crack growth behaviour? If you're doing a normal short crack fatigue experiment, the only information you would get would be the red curve on the bottom left. That's your surface observation. So if you were trying to get data on crack growth rates for short cracks in magnesium using conventional techniques, that's all you would have. And it's telling your crack growth rates around about 8 nanometers per cycle under these conditions. Tomography gives you depth as well, and it's around about the same. It starts a bit shorter, but the crack growth rate's around about the same. If I remember correctly, that's about 7, that's about 9. But because you've got the local measurements of the crack front, you've also got three-dimensional information, you can get the local crack growth rates. And I'll bring those back up in a couple of slides' time, because that's what's more interesting. Because what is the relationship between the orientation of the crack, the loading it's seeing, and the crack growth rate? We'll just divert into the serial sectioning. It's just giving you an idea of the kind of data. So the video in the middle is the experiment in progress, in a sense. Let's let it run for a few seconds. It's not perfect, you lose bits of material every now and then, you can see the flakes going off. When you put the data back together, you can essentially do fractography on your data set. I haven't got time to go through all the information you get from this, but we're going to focus our attention on this part of the crack, where it's clearly very crystallographic. I'll look at what's going on there. There's some very interesting stuff going on here. There's a bit of twinning going on here, and the crack's interacting with the twins, and that's affecting the crack growth rate. So you can just see the twins there. Those are in the paper. Down here, you're seeing a comparison between what X-ray tomography will tell you is going on and what the sealed block face sectioning is doing. But it gives us confidence, coming to the sectioning, to try and identify the mode of fracture we're getting there. And here, the crack is propagating along the basal plane, as you see in the moment. That was actually stuff we did a few years ago. We published that as an analysis. And then we got interested in image correlation and had the software to do image correlation, the three-dimensional image correlation. So we went back, looked at the data again, to say, well, could we measure something more from this data set? So on the left, you're seeing the displacement field. This is the vertical displacement field. On the right, just for visualization, is the strain field. And during my preference for using image image correlation, any form of image correlation, is I'll use strain for visualization, but I'll always go back to the displacement field. The displacement field is the data. The strain is usually much noisier, it's just the gradients, displacement fields, and some of the ways the software calculates strains are not necessarily the best tools for doing it. What we're going to look at is just one particular part of the crack. Here's a notch, and it's the crack that was growing, as we've seen in moments, it's growing along the basal plane. And because you've got tomographic data, we can look at the region before the crack went through it, and then we can look at the crack which then propagated through here. Try and ask the question, what is the mode of opening of that crack? So if you want to try to model its short T-crack growth, the various crystal plasticity models around, one thing you want to use to validate those models is, well, how's the crack behaving? So, look at one particular, let's just where we're going to look. Right, so for the early analysis, because you've got the crystal grain orientations, you've got the crack orientations, you've got local crack growth rates, it's just the data projected. You can see, for example, here we've got a very fast local crack propagation rate. It slows down here because the crack kinks. This is giving us the orientation of the crack, and this is telling us that the crack is very close to the basal plane here, whereas where it slows down is where the crack plane has changed. This is just showing the actual basal plane orientations. Again, three-dimensional information. And maybe the last slide is because you can measure the displacement field in 3D, we can take the crack that we're interested in. We know the three-dimensional orientation of the crack. We have the full displacement field. We can measure the displacements perpendicular to the crack plane and in the crack plane and say, well, is it mode 1 opening? Is there any shear going on? This is the measurements that you take before the crack's gone through that bit of region. That's basically the noise, the measured uncertainty. This is what we get when we look across the crack. We just do it in terms of the gradients. We get strain, apparent strain. That's telling us we found the crack. And essentially this point here is showing that we get a displacement change across the crack of the order of around about a micron and a bit. And this particular crack, even though it's growing crystallographically, because of the full shape of the crack, it's basically just opening. Even though it's an inclined crack, and the loading we're applying because of the orientation of grains, it's a mode 1 opening crack. Yeah? What that means is something to work out, is that we can actually measure it. Yeah? Because generally when you see a crystallographic crack and a short fatigue crack, the assumption is, oh, it's a shear mode. It's not necessarily so. The only way you can be sure of that is to do these types of experiments. So, time's up. So we're saying, see the techniques go in play.